Hello everybody, I am Professor Yogesh Chaba from Guru Jambeshwar University of Science and Technology, Hisar, Haryana. Today in this lecture, we will study about Advanced Encryption Standard AES. This lecture on AES has been divided into three parts: Introduction, AES algorithm and modules of AES. AES algorithm was published in 2001. Prior to AES, there was DES, which began approaching the end of its useful life within few years of its inception. NIST, National Institute of Standards and Technology, the agency of the US Department of Commerce, decided that the government needed a new cryptographic standards for unclassified use. In order to do this, NIST sponsored a cryptographic bake-off contest. In January 1997, researchers from all over the world were invited to submit proposals for a new standard to be called AES, Advanced Encryption Standard. The rules for designing AES algorithm were that the algorithm must be symmetric block cipher. The full design must be public. Key length of 128, 192 and 256 bits must be supported. Both software and hardware implementations must be possible. The algorithm must be public or licensed on non-discriminatory terms. In August 1998, NIST selected 5 proposals as shown in figure, primarily on the basis of their security, efficiency, simplicity, flexibility and memory requirements. Out of these 5 proposals, Rinedol was selected, and in November 2001 it became a US government standard and was published as Federal Information Processing Standard FIPS 197. Rinedol was designed by 2 young Belgian cryptographers, John Damon and Vincent Ridgman. Rinedol supports key lengths and block sizes from 128 bits to 256 bits in step of 32 bits. The key lengths and block length may be chosen independently. However, AES specifies that the block size must be 128 bits and the key length must be 128, 192 or 256 bits. It was doubtful that anyone will ever use 192 bit keys. So, AES has practically 2 variants: a 128 bit block with 128 bit key and a 128 bit block with a 256 bit key. In this lecture, the algorithm we will discuss will have only 128 bit key with 128 bit block data. A 128 bit key gives a key space of 2 to the power 128 keys. Even if NSA manages to build a machine with 1 billion parallel processors, each being able to evaluate 1 key per picosecond, it would take such a machine about 10 to the power 10 years to search the key space. Now, let us move over to Rinedol algorithm. From a mathematical perspective, Rinedol is based on Gillis field theory, which gives its some provable security properties. Like DES, Rinedol uses substitution and permutations, and it also uses multiple rounds. The number of rounds depends on the key size and block size, being 10 for 128-bit keys and 128-bit blocks. These rounds may move up to 14 for the largest key or the largest block. However, unlike DES, all operations involve entire bytes to allow for efficient implementation in both hardware and software. An outline of algorithm is given in figure. First of all, 128-bit key is expanded into 11 states as a 4 byte by 4 byte matrix. Then XOR operation is performed on first key. Then substitution, rotation, mix function and adding of round key operation is performed with rest of 10 states of key. Now let us see how exactly this algorithm has been implemented through software. Please see the figure. This function Rinedol has 3 parameters. They are plain text, which is an array of 16 bytes containing the input data; ciphertext, which is also an array of 16 bytes where the n ciphered output will be returned; and third is 16 byte key. During the calculation, the current state of the data is maintained in an array state whose size is n rows by n columns. For 128-bit blocks, this size is 4 by 4 bytes. With 16 bytes, the full 128-bit data block can be stored. Algorithm Rinedol is as shown in figure. The state array is initialized to the plain text and modified by every step in the computation. The code starts out by expanding the key into 11 arrays of the same size by using expand key function. They are stored in RK, which is an array of structure, each containing a state array. One of these will be used at the start of the calculation and the other 10 will be used during the 10 rounds, one per loop. The next step is to copy the plain text into the state array, so it can be processed during the rounds. Then RK0 is XORed into state byte by byte. In other words, each of the 16 bytes in state is replaced by the XOR of itself and the corresponding byte in RK0. Now it is time for the main loop execution. The loop executes 10 iterations, one per round, transforming state on each iteration. The contents of each round consist of 4 steps. Step 1 does a byte for byte substitution on state. Each byte in turn is used as an index into an S box to replace its value by the contents of that S box entry. This step is a straight monoalphabetic substitution cipher. Step 2 rotates each of the 4 rows to the left. Row 0 is rotated 0 bytes, row 1 is rotated 1 byte, row 2 is rotated 2 bytes and row 3 is rotated 3 bytes. Step 3 mixes up each column independently of the other ones. The mixing is done using matrix multiplication, in which the new column is the product of the old column and a constant matrix. Finally, step 4 XORs the key for this round into the state array. At the end, the contents of the state are returned as the cipher text. Since every step is reversible, decryption can be done just by running the algorithm backward. However, there is also a trick available in which decryption can be done by running same encryption algorithm using different tables. A pictorial view of algorithm explained just now is shown in figure. First is byte substitution, which is a simple substitution. Second is shift row, in which the rows are permuted by left circular shift by shifting the leftmost high order elements to the right and low order elements in last. Third is mix column, in which a complex transformation on the columns is applied. Finally, round key derived is added to each column. This sequence is repeated for a number of rounds depending on the key length. Now, let us move on to more details of main 4 operations in AES algorithm. AES is a block cipher of block size 128 bits. The key length can be 128, 192 or 256 bits. It is convenient to think of a 128 bit block of AES as a 4 by 4 matrix called the state. State is presented as a matrix S00 to S33. The state is filled from the input in columns. Assume, for example, that the input is the 16 byte B0, B1, B2, B3 up to B15 as shown on left side of table. These bytes are then represented in the state as shown on right side of table. Some operations in Renedol are performed on columns of the state and some on rows, so that this representation implements a form of transposition. Now, let us discuss each step of this algorithm in detail. First step in Renedol algorithm is byte substitution. Byte substitution is a conventional substitution box. Each byte is replaced by the byte which is the result of the two mathematical steps. First is to take the multiplicative inverse of B in GF 2 to the power of 8. Second is to XOR that result with 0, 1, 1, 0, 0, 0, 1, 1. The complete substitution table is as shown. For example, the byte 20 is replaced by B7 as it is in row 2 and column 0 of the table. Similarly, 5A will be replaced by BE as it is in row 5 and column A. Now, moving over to second step, which is shift row. In the shift row step, assume a block is composed of 16 bytes numbered from left to right or most significant bit to least significant bit. In the shift row operation, the numbered bytes are shifted to the position as shown in table. That is, for 128 and 192 bit blocks, row I is rotated left I minus 1 bytes in the table. Table A shows shifting for 128 bit data and table B shows shifting for 192 bit data. Accordingly, in table A and B, we can see that row 1 has been rotated left 0 step, row 2 has been rotated 1 step, row 3 has been rotated left 2 steps, and row 4 has been rotated left 3 steps. We can see that 3, 7, 11, 15 in row 3 has been converted into 11, 15, 3, 7 by shifting left 2 steps in table A. For 256 byte blocks as shown in table C, row 1 and 2 are shifted I minus 1 step, but row 3 and 4 are shifted 1 extra step, that is I step instead of I minus 1. After shifting operation, let us move on to third step, which is mix column step. In the mix column operation, each column is multiplied by the matrix of 4 by 4 dimension as shown in figure. First row of matrix is 2, 3, 1, 1. Second row is 1, 2, 3, 1. Third row is 1, 1, 2, 3, and fourth row is 3, 1, 1, 2. This matrix is multiplied by each column and result is obtained. The final step in each loop is to XOR a variation of the key with the result obtained so far. The variation is as follows. The first key is the key itself. The second key is changed 4 byte word by word. The first word is rotated 1 byte left, then transformed by the substitution of the byte substitution step, then exclusive ORed with a constant. The rest of the words in that subkey are produced by the exclusive OR of the first word with the corresponding word from the previous key. So, this was AES algorithm. We have observed that despite all this complexity, AES is basically a mono-alphabetic substitution cipher using long length characters of 128 bits. Whenever the same plain text block goes in the front end, the same ciphertext block comes out the back end. If you encrypt the plain text 100 times with the same key, we get the same ciphertext 100 times. An intruder can exploit this property to help subvert the cipher, but still till date no significant problems have been found with Renaudot algorithm used in AES. So, finally we can say that AES seems to be a solid replacement for the DES. So, friends, this was AES algorithm for symmetric key cryptography. We studied introductory part of this algorithm followed by detailed working of steps of this algorithm. Thank you.